So I was asked to talk about rotational seismology, and the work I will be presenting here is definitely not only my work, it's mainly from other people. Too many to list here, so you'll see references and names and images throughout the presentation. And my intent is to give you sort of a teaser of what's possible with rotational seismology, and hopefully also make clear what it actually means and why it could be interesting to take into account not only the three components of translation that we typically measure with broadband seismometers, but also the three components of rotational motion. So here on the first slide, you see two waveforms. They look pretty similar, but if you look closely, there are some small differences. And in fact, the black one is a recording by a traditional broadband seismometer, so it's transverse acceleration. And the one at the top is actually a recording of the associated rotation rate for the same event. So you see that there are some similarities of the waveform and some small differences, and those aspects can actually be exploited to get information about a bunch of different things. So what is this rotation anyway? So most of you will probably have looked into a seismology textbook at some point, and there you will have a description of how to determine or describe the ground motion, and that will typically be something like this. So first of all, you have this thing that's usually written as a U, which is your translation motion. So let's say ground acceleration, and that's typically measured with the seismometers that we are familiar with. Then we have 6 components of strain, with epsilon here being the strain tensor, and we'll have talks about how we can measure those with dust systems, for example. And then there's this last term in red, which is actually the curl of the wave field, and that is the 3 components of rotation that are associated with any like infinitesimally small displacement from an elastic wave field. And typically in textbooks this will be mentioned, but then disregarded immediately. I think in Aki and Richards they even explicitly say something like, okay, this is cool, but we can't measure it anyway, so let's just ignore it. Okay, maybe a bit more subtle than that, but essentially nowadays we have ways to measure this rotation rate. And there's been a lot of work done over the past 20 years or so to try to explore what kind of possibilities that unlocks. There's a couple of nice review papers if you want to know a bit more about this kind of description, derivations of the rotation exactly, etc. Felix Bernauer, one of the people working a lot on measuring rotations, created these cool little animations that show what the rotations look like. So here you see a representation of the ground acceleration, so the transverse motion or translation motion. And here on the right, you see the associated 3 components of rotation motion. And this is actually from a recording of an earthquake, I think in Italy. So this is real data to show that seismic waves do have rotational components as well. I'll talk a little bit more about that later. All right. So what I want to do today is tell you a little bit about possible applications. And as Anpo pointed out earlier, we typically have to argue why this stuff is societally relevant. And I think the main societal relevance of rotation motions is in structural engineering, because rotation motions can induce, for example, torsional modes in buildings that can be quite destructive. But for people who are just curious about seismology and the Earth and what's happening under our feet, there are also a lot of things that we can extract about the source of seismic waves, about Earth structure, and about the wave field in general. Okay, I'll touch on all of these topics, but first I want to tell you how we can actually measure these rotations. So a bit about the instrumentation. So really bird's eye view. Essentially there are 3 different ways to record rotational motions. The first one, and this is how it started, is with these big observatory instruments. This is the first one I think that recorded, or that, where we have papers that show seismological recordings of rotation. This is the Wetzel ring laser. So these instruments are typically built for geodesy, to look at the rotation rate of the Earth as a whole. And then it turned out that they had this annoying noise every time there was an earthquake. So they contacted a seismologist, like, what's up with this? And turns out that it can be actually interesting for us. Then there are some, not a lot, but there are some portable field instruments, because in seismology you don't want to just be necessarily tied to one spot with one of those huge observatory instruments. And then there's also ways to use very dense arrays of seismometers to extract rotation motion. Okay, so first, these observatory instruments, they're called ring lasers, and essentially what they are optical interferometers that use what we call Sagnac interferometry. And there's a book written about it, so I'll just give you really the basics here. Essentially, what you have is a laser beam that is split into two, so it starts in phase, it's split into two, and it's sent into what they call a cavity, which is, in this case, essentially just a ring or a square with mirrors here at each corner, bouncing the light in a square. So the laser is split in two, and one beam goes that way, and the other beam goes that way. Okay, that's it. The laser light interferes with itself, and that interference is with a specific beat frequency that we call DF typically. All right, so you have the system with the two counter-propagating laser beams, one in red, one in blue here for illustration purposes. And if you move this whole system transversely, so like what you would typically, the motion you would typically measure with a seismometer, what happens? So the red laser beam, so the one going in one direction, essentially has a slightly longer path length here to catch up with the mirror that's moved in the meantime. This length stays the same. This length is a little bit shorter from the point of view of the light because the mirror moved towards it. And then it ends up, at the starting point. And for the laser beam going in the other direction, it's, well, opposite effect, but it's the net result is the same. So you don't have a change in the path length between the two laser beams, which means that the interference frequency of that light stays the same. So the beat frequency stays the same. All right, that clear? Then what happens if you take this whole system and rotate it a bit? Then the laser that's going in one direction basically has to catch up with the fact that the mirrors have moved away from it. So it has to, it has to travel a slightly longer path than it did in the original situation, and the beam going in the other direction has the opposite effect. So the mirrors are moving towards it. So it has a slightly shorter path to cover to get back to its original point. So that means that we now have two different path lengths for the two laser beams, which means that the interference frequency will change, and that change in interference frequency is related to the rate of rotation of this whole system. So I hope that it's clear from this that this kind of measurement principle makes a system that's not sensitive to changes, translational changes, but it is sensitive to rotation changes uniquely. Okay, so this is the kind of measurement principle that's implemented in these big observatory systems. Of course, there's a bunch of cool laser physics, metrology, I don't know what going on to make these work. And the fact that they're so complicated and expensive to construct and maintain means that there's not so many of them out there. Currently, I think the count is about 6 worldwide, not all of them operational. There are 2, now 3 in Germany actually, and then in Christchurch there are 2, I think, in Pisa and Gran Sasso. There's another one. So yeah, not so much to work with. The two main ones that are providing data for seismology at the moment are the G-ring in Wetzel. That's this one. This is the first one that was used for seismology. It's a square of 4 meters by 4 meters, so pretty big. And yeah, on a zero-dur plate that's usually used for telescope mirrors. It's super expensive stuff to keep everything rigid in place. Yeah, so that one's located around here on the Czech border. And then there's a reasonably new one that was built next to Munich in the observatory there. And that's called ROMI. That's even bigger. It's triangles now because to optimize the space a little bit. Triangle interferometers in 4 of them in a tetrahedral constellation. So with that, you can measure 3 components of rotation. So the first component of rotation that you measure is basically with the horizontal triangle. When it rotates, it measures rotations around the vertical axis. And then with the 3 ones that are sort of in this pyramid shape below, you can compose the horizontal components of rotation. So with that, it's the first like big 3-component rotation sensor worldwide. And it was a huge operation to build this. They had to dig a, I think, 20-meter deep hole to put that whole installation in. All right, so those are the observatory instruments. As I said before, there are only a handful of them, and in seismology, you typically want to go out in the field and do measurements over there. So there's a big push to try to get companies to develop portable sensors. And that resulted in a couple of different variants, but one of them that works quite nicely is the Blue size by formerly IX Blue. Essentially, the measurement principle of these guys is the same as for these ring lasers. It's the same kind of optical interferometer, except that they send the laser light into optical fiber, wrap that around to make it smaller, and then put that in one of these devices. They're about yay big, weigh 25 kilos, need a lot of power to run, but they are portable, and if you're strong enough. And they have 3-component measurements. So you can get 3 components of rotation measurements with one of those. Then, if you don't have one of these fancy devices to your disposal, but you do have a very dense seismic array, what you can do is use the seismometers together to extract the rotation rate. And the principle there is that you need sensors that are closer than a quarter wavelength together, and then you can basically measure the spatial difference in motion between the sensors to get the rotation of the whole array around a central point. So that's a little bit finicky. There's a lot of assumptions going in there, but it works. And there's one study at Pinion Flats Observatory done mainly by Stefanie Donner, where we used the pretty small array at Pinion Flats. So here it's a bit of a busy picture, but essentially the dots are seismometers. So there's a sort of large version of the array and then 2 smaller constellations of groups of seismometers. In the middle, at that time, there was a small ring laser operational. So we have some ground truth about what the rotation rate should be. And then at Pinion Flat, it's famous for the strain meters that are there as well. So comparison, the traditional seismometer measures this when there's an earthquake. I think it was in Mexico. Then the ring laser measured this waveform for rotation. And by using the seismometers around it and doing this spatial differentiation, essentially, you can get this signal for what we call array-derived rotation. And visually it looks similar, but if you calculate the correlation coefficients between the 2 signals, it's pretty good. And then what you can also do if you have a small group of seismometers together like that is calculate that other spatial gradient, which is the strain. And you can also compare that then to the direct measurement of strain with a strain meter. And again, that works. So we have these 3 different ways to measure rotations. So we can go forward and see what we can actually do with those measurements. All right, and I'll start with what we can find out about the wave field itself. Because one of the nice properties of these rotations is that it works as a wave-type filter. That's, again, nicely illustrated in this animation by Felix Bernauer, where here you have the 3 components of translation for P wave, SV, etc., and then 3 components of rotation. And as the P wave goes by, I'll start it again in a second, you see that you have some translation motion, but you don't have any associated rotation, or you shouldn't really, because it's just a compressional wave. There's no curl involved. For the SV and SH waves, you have a bit of associated rotation. As soon as you have shear, you have some rotation in there. And for love waves, you would expect to have rotation around the vertical axis from this sort of horizontally polarized shear motion. And for Rayleigh waves, you have rotations around one or both horizontal axes from this retrograde elliptical motion. Let me see if I can start that again. So here you see the block moving for the P wave, just up and down. SV wave is not really rotating. SH, there's a bit more of a twisting motion in there if you look carefully. And then for love wave, it becomes more clear that there is some rotation of the block. And Rayleigh waves is twisting all over the place. All right, so that means that if you have a rotation sensor, you can pretty easily differentiate the love waves in your wave field from the Rayleigh waves and the upgoing, downgoing S waves, for example. And that's something that was done by David Solberger at ETH. There's another paper that I did not put here, where he exploits this property to do polarization analysis on seismic wave fields. So essentially using these 3 components of translation, 3 components of rotation together to unravel which part is the S wave, the Rayleigh wave, and so forth. One small example is, oops, spoilers, is if you look at the recording, the 3-component, just transverse recording, classic recording of, I think this was an upgoing S wave. From those 3 components, you can extract the incidence angle of the wave. That's pretty classic stuff. Now, if you add in the 3 additional components of rotation, not only is the incidence angle hit better, so it's better determined, but one of the magical things that I'll explain in a second is that you can also extract the local phase velocity of that wave. So, all right, I think I'll leave it at that for the wave field aspect. So we've seen that we can separate the wave field into its different wave types. If you go one step further, you could also look at wave type ratios, which could be interesting for equipartition, for example. Yeah. So what can we do with that? Let's look at structure. So I just pointed out this fact that you can get the local phase velocity. How does that work? Now, if we think about just a plane wave that's moving along, and we measure that with, we measure the translation of that plane wave and the rotation of that plane wave at the same location, then the very simple version is something like this. So our plane wave is a sine wave. We can then look at the transverse acceleration, so double time differentiation, and the perpendicular rotation to that, so the rotation around the vertical axis. Why those two? Because those two represent what a love wave does, essentially. So a love wave will have a transverse component on the translation motion, and it will have rotations around the vertical axis, right? So you can then combine the expression of those two and see what happens. And it turns out that, most of this cancels out. What remains is just 2 times the phase velocity. So what does that mean? If you have the measurement of transverse acceleration and vertical rotation rate at the same location, you just need to look at the amplitude ratio between those 2 waveforms to get the local phase velocity, something that you would usually need an array for. And something else that we can see is that the two waveforms have to be in phase. And with that property, you can extract the back azimuth, so basically the direction towards the source. So just with these two measurements, you can already extract a lot of what's going on with the wave field. Yeah, okay, so again, you can get the local phase velocity, which gives you information about structure. The fact that the waveforms have to be in phase means that you can immediately get information about the source direction. And people tried this out. Oh, right, first. This is from Moritz Bernauer and Andreas Fichtner and some others, calculated what the sensitivity kernel for this combined measurement would be. So at the top is a sensitivity kernel for just the velocity, for the translational motion. You get this sort of classic banana donut thing. For rotation, it looks pretty similar. But if you look at this combined measurement, so the amplitude ratio between rotation and translation, you see that it's mainly sensitive around the measurement location, so the local structure, and a little bit sensitive to the source. What's pretty cool about this is that you don't actually need information about the source time or the source magnitude. You just look at the amplitudes of the waveform that's coming in. That's enough, so you don't need travel times and stuff like that. What you do need is very accurate amplitude information, and that's something, as most of you might know, where it gets a little bit tricky in seismology. But in principle, it's a pretty powerful measurement. So we're sensitive to the local subsurface structure, and that means that with a pretty easy operation, you can get things like dispersion curves from your measurements of translation and rotation together. This is an example from quite a while ago by Dieter Kurle, where he just created dispersion curves of a teleseismic event. You've all seen dispersion curves before. So here you see the group velocity quite nicely, and the line, the profile here, the velocity profile of the apparent phase velocity was obtained just from the ratio of the rotation rate here in red and the transverse acceleration from one measurement point. So it works. And this kind of analysis can be used for example, microzonation. Think about in cities where you don't necessarily want to or can install a bigger array of stations to get the local subsurface structure. If you have just a single station that measures these 6 components of motion, you can do this operation, take the amplitude ratio, extract a dispersion curve, and then just invert for the local velocity profile. This was done in, I think she did it in Munich mainly, for a bunch of locations by Sabrina Keil. And what she also did is compare this single station method to more established methods like SPAC, explained by Michel earlier. And I don't remember what the long version is of HRFK, but yeah. And you see in green here that this is the dispersion curve of phase velocity obtained with a single station with rotational measurements and translation combined, works nearly as well as the established methods, but with a lot less logistics and in places where it might not be possible to install an array. Okay, so that's one possible application area. We saw earlier from the sensitivity kernel that we're mainly sensitive to the local structure, and that is something that was explored by Sneha Singh a couple of years ago during her PhD. She wanted to figure out how sensitive these rotation, or more generally gradient measurements, are to local heterogeneities. And what she did to do that is numerical experiments where she started first with just a homogeneous model and put 4 measurement points, stations, really close to each other. And if you have an earthquake somewhere happening off screen there, the signal recorded by those 4 stations will look exactly the same for the displacement, but it will also look exactly the same for the rotation. Now, if you introduce heterogeneities here, so here just really strong heterogeneities right next to those stations that are measuring it, the picture changes a little bit. So the heterogeneities introduced here are about 1/3 of the wavelength, pretty small. And if you look at the waveforms, yes. If you look at the waveforms, the displacement measurement doesn't care about those heterogeneities. The 4 stations still measure the same thing. But if you look at the rotation rate, so one of the spatial gradients, you see that the 4 stations here measure something quite different. So that means that those rotation measurements are really sensitive to local heterogeneities, which can be a good thing or a bad thing depending on what you're after if you're doing tomography, for example. This, by the way, also applies to DAS, which I thought I had a... Go on. There? No. That's something else? Somebody else. Okay. There's a study by Jan Capdeville and Anthony Sladen recently in Seismica, where they explored this aspect for DAS measurements, so for strain measurements, and they find similar effects. There it is. Okay. And Mirko, where are you, Mirko? There he is also working on these questions. So if you want to know more about it, you can go talk to him. All right. So that's about structure. We saw that we can get the phase velocity pretty easily from amplitude, ratio, dispersion curves. We've seen what the sensitivity kernels for that measurement, for that observable looks like, and we've seen that we can be really sensitive to local heterogeneity. Now, moving on to the next aspect, which is the source. How am I doing on time? Okay, I think I'll... there's advantages when you want to look at earthquake source inversion. I think I'll skip this unless people complain. If you have questions about this, I can loop back to it at the end. The main message is that if you have 6-component measurements, you can actually better constrain the focal mechanism of earthquakes with an array that's half the number of stations. So again, in the sense of logistics, that can be quite interesting. Then back to this slide. So this property that if you look at the transverse acceleration and the rotation rate around the vertical axis, the 2 waveforms have to be in phase and give you the phase velocity. So this point that they have to be in phase, that can be used to retrieve the back azimuth towards your source. And that's something that I did here. So this is an example of the Tohoku earthquake recorded with broadband seismometer and with the ring laser in Wetzel. So here, yeah, you have pretty nice strong signal on both. And what I'm going to do now is essentially keep the rotation rate signal or waveform as it is, and then take the horizontal components of the broadband seismometer and do a grid search across all possible back azimuths. So you basically rotate your horizontal components to point at, let's say, north, and then at 90 degrees, and etc. And at each step, you compare the waveform of your horizontal component to the waveform of the rotation. If they line up, if they're the same waveform, that means you're here, and that means that you're pointing towards the source of those seismic waves. So this is the plot that's going to be filled in with essentially the range of back azimuths over the course of one day. And for each possible back azimuth, the correlation coefficient is measured, calculated to see how well the 2 signals match. And here in red is correlation coefficient of 1, which appears for a back azimuth of, what is that, 30, 40 or so, essentially in this direction, which matches with the expected direction towards the Tohoku earthquake. So that works. If you then look at the rest of the day and filter between 0.1 and 0.2 hertz, it looks like this. Because at that point, you're looking exactly at the secondary microseism, which Fabrice talked about this morning. And from the point of view of this station at that time, it typically comes from the North Atlantic, from somewhere south of Greenland. So that corresponds to the back azimuth that we pick up here. And so that fits as well with what we expect. So that seems to work. And we've essentially repeated this type of analysis using the pinion flat observatory and the array-derived rotation there that I mentioned earlier to look at what the ocean microseism looked like for over a year. So that's what you see here. You can get the rotation rate around the vertical axis to extract the love waves in your microseism field, and then you can take the horizontal components of rotation to get to find out where the Rayleigh waves in your microseism field are coming from. So this is what we get for secondary, primary love waves, secondary, primary Rayleigh waves, and just to make sure that that's what's really happening, we compared that to beamforming with an array just south of Pinion Flat, because you need a slightly bigger amplitude aperture to get beamforming there. So overall, they match pretty well. And this will be published pretty soon, so keep an eye out if you're interested. The main point here is that this, let's say, rotation beamforming with a single station works reasonably well compared to actual array beamforming. And the second point is that we do pick up the ocean microseism on the rotation components. So everybody sitting here who's used to doing ambient noise correlations probably now thinks, what about the correlations of ambient noise? At least I thought so, so I tried it out. And I think this has been explained a couple of times now, so I'm not going to go into it. I'm going to assume that everybody knows what an ambient noise correlation is. So the question is essentially, will this also work for rotation motions? And that question was answered in theory by Le Tang. And if you want to look at that, there's a nice publication in GGI last year. But does it also work with data? So first of all, you need data where you can pick up the microseism at two different locations. And that's where it was tricky for a while, because we only had one ring laser that was sensitive enough to pick up the secondary microseism. Then this other ring laser, ROMI, was built, and once it was operational properly, there were days where it could also pick up the secondary microseism quite well, which is what I'm showing here. So this is just one example of an hour. Again, same type of plot as before. You can see that you have very nice correlation between the rotation rate and the transverse acceleration, showing that you're pointing towards the secondary microseism there. And we say the same thing, a little bit noisier, for the ROMI ring laser. So we do have ambient noise recorded at both of those locations. And then we can have a look at what the noise correlation looks like. So first here, just with the classic seismometer to see what we expect. I didn't mention yet that we are focusing still on the rotation rate around the vertical axis, so that means that we're picking up the love waves in the ambient noise field. So we compare the rotation stuff later on to the transverse component of the correlation. And that's what it looks like for two broadband seismometers that are at each of those locations. With here, the causal component from basically waves propagating from ROMI to the Wetzel ring laser, and that is waves propagating from the Wetzel ring laser to ROMI, bit lower amplitude because the noise sources are mainly on this side. So that makes sense. Okay, I think that's established that we can do that with normal seismometers. Now, this is what it looks like when you look at the recordings of rotation directly. So we expect the two waveforms to be similar shape. So the waveform of this vertical rotation rate should be the same as the one of the transverse acceleration, so that fits. And just as another sanity check, I looked at what the synthetic love waves in PREM should look like and what kind of arrival time they would have, and that overlays quite nicely as well. So this is mainly just a proof of concept that noise correlations with rotations actually works. And I didn't yet get to publishing this, but I probably should write it up at some point. Okay, so that wraps up for now the wave field part. I've added the ambient noise correlations to wave field. It could also go under structure. And we've seen before that in terms of source, we can extract direction towards source. We can pick up microseism, but we could also do, for example, source tracking with just a single station. And that has been done for rupture tracking of earthquakes, for example. All right, so now moving to structural engineering, where the thing I pointed at the very beginning, because I think that that is a space where rotation measurements as they work now can bring some advantages. So the results I'm going to present here are from a project called Giotto, which is a collaboration between University of Hamburg, LMU, and BAM, the Materials Testing Institute in Germany. And the project was about how we can use rotation measurements to get better information about civil structures, about buildings. And one of the questions in that project is, where do we expect the largest rotation motions in a structure to happen? Because you would expect damage to start occurring there. And here what we did is look at the eigenmode shapes for rotational motion on a small test structure that's part of this BAM institution. The test structure is essentially I think it's 24-meter long concrete bridge structure with 3 supports. And we put 4 stations on there. So the stations each time are 1 translation sensor, just a Trillium compact, and 1 rotation sensor under each of these white boxes. And then we did some stuff to the structure to make it respond. So one of the things we did was gradually increase the load on the structure from 300 to 900 kilograms. And a nice, that broke. A nice property of the structure, come on. No, it's gonna, well, you don't see the image, but is that you can change the pretension on the bridge. So basically by pulling on the steel reinforcements that are in the bridge structure.